Let's go. So let's do another problem, but now we're going to start discussing a general form of this power series. Instead of having to build it up each time, which I imagine you've been watching and paying attention, you're like, do I just do this every time? No, not really. There's actually something, some old dead dude named Taylor came up with something called Taylor polynomials. I guess. I don't know. I haven't actually looked into it. I usually like to look in and see if they actually came up with it, or maybe it was just some rich dude that got his name on it. So here it is, and you're like, oh my goodness! Why is there so much written there? Taylor polynomials. But what I'd like to do at first is just go, hold on. Let's just ignore this. Let's just ignore the top. Let's look down here. So we're talking about an nth order Taylor polynomial centered at A, and this is the general form. This is our big old general form, so we don't have to build those power series any longer. Like, look, here is our first degree. All right, you remember this, don't you? Don't you? That this is, mx plus b, that being the slope, that being your x value. It's just a line. So that would be the linear approximation. If we were to go one more term, this would be the quadratic approximation. If you were to go another term, that would be the cubic approximation, and so on, all the way down to our new fancy formula. Now, they write it in more compactly as the sum is k equals 0 up to n of some c sub k times x minus a all raised to the k. But you're like, dude, I already knew that part. We've already done that. You've already told me that. Yes, cool story. But now we know. Now we know what those coefficients are out front. It's going to be the kth derivative, whatever term you're on. If we're on the fourth term, it would be the fourth derivative with a plugged in, divided by 4 factorial for each one of these terms. So now we have something. I personally don't like the way they write this. This is what we're going to do next. We're going to use Taylor expansions. I would rather say that, oops, maybe you don't like this. Maybe it's too much in one. Where it gives the sum, k equals 0, and how it just writes in c sub k. I would write in c sub k. It's the nth derivative. Actually, it's the kth derivative, my bad. I get those backwards too, because k is our indice. The kth derivative at a, all over k factorial times our x minus a to the k. I prefer that, where they just wrote c sub k in there, and then you're supposed to know what it is. That formula right here gives you everything. You're like, I have to memorize that? Yes. Yes, you do. Welcome to calculus. Calc 1, not so tough. Not so tough. Now looking back at it, huh? How tough was Calc 1? Looking back at it. You're like, no, I kind of wish I was back just doing derivatives instead of doing Taylor polynomials. Why won't that erase? There it goes. Okay. Let's do a problem. We are going to find the Taylor polynomials. Oops, bring it down. First degree, or a linear. A second degree, a polynomial. Or a quadratic. Third degree, cubic, and so on. But we're going to center it around x equals 0, which is really nice for us. Because you see all these x minus a's? These are now just x's, because a is 0. But before we ever even get into this, we're going to have to find our first degree. All right, that's our first degree. We know that one. But then we're going to have to find a second degree and a third degree and all of this. But what's going to be in here? Sorry. I'm not going to write this the next time. We're going to need to just keep adding on to it. So then this would be the same thing, the same thing, the same thing, plus, and then it would be f triple prime of a over 3 factorial 6 times x minus a all cubed. But do you see, the only thing we really have to solve is for the derivatives. We continually have to put in more and more derivatives. So why don't we go through and let's just start differentiating sine first. So I'm going to jump off to the side and take sine. All right. f of x is equal to sine of x. Let's go find our derivatives, because this question is asking us to find it all the way up to the 7th. So first derivative, cosine. Second derivative, negative sine. Third derivative, we're going to go to negative cosine. And then our fourth derivative, and this is the way they write it, with just a little parenthesis around it. And that's going to be positive sine. And then it's going to wrap back around, huh? You're going to repeat the process. That's cosine. Oh, man, you're like, why are we doing such a long problem? Wait till you go to Calc 3. Wait till you go to DE. You think these are long problems? So now what we'd like to do is we're going to need to plug in 0. We've got to plug in 0. So we're just going to jump over here and be like, well, what are all of those when you plug in 0? Because that's what we want. We don't actually care about the actual function. We're like, well, what's f of 0? That's 0. What's f prime of 0? Cosine of 0? It's 1. F double prime of 0? Still 0. F double prime of 0? Well, that's going to be negative 1. And then we get, that's triple prime. The fourth derivative at 0 is going to be 0. Do we see that we're just oscillating back and forth? Cosine of 0 is still 1, and then after the 6th of 0 is equal to 0, and then after the 7th derivative of 0 is going to be negative 1. So we see that we just went back and forth, back and forth, back and forth. All right. Oops. I'm going to show you all that yet. Dang it. I failed. I want to hide that. So why don't we go and set this thing up? I just want to go. I don't want to do the first. I want to just do this thing. Let's get it. So we're going to say our polynomial expansion here is going to be, so for our first one, what was that again? Oh, it's f of a plus f prime of a times x minus a, where a is just 0. So we're like, all right, so this is f of 0. This is f of 0 plus f prime of 0 times x minus 0. Well, what was f of 0? That was 0. So this is 0 plus 1, right? F prime of 0 was 1 times x minus 0. So our first degree, we're like, you can just model it with x. There's your linear approximation. It's just y equals x. It's not a very good approximation, does it? That's not a very good approximation. Well, I don't know. So like right here, looks pretty good. Huh? I mean, geez, with just one of these, we get a pretty good approximation near 0. Near 0. And then let's go and let's do our second degree. Let's do our second degree. Jump off to the side so we can see it. We're like, okay, let's do our second degree. So we're like, okay, so that's f of 0 plus f prime of 0. Sorry about my alarm. I'm watering stuff in between. Video x minus 0 to the first. And then it says, over 1. And then it's f double prime of 0 over 2 factorial times x minus 0 all squared. So what's this turn out to be? That's still 0. We've already solved all of this. This is 1 times x minus 0. Plus, what's f double prime of 0? Oh, it's 0. So that just goes away. So our second term, it's actually not a quadratic. I thought it might be, but it's not. It's just x. It's weird. It's almost like all the evens just turn out to be the same one as the previous odd. Look, 0, 0, 0. So we're only going to have new terms on our odd approximations. So we're going to do it one more time. Actually, that's not a lie. We're going to do more. So it's f of 0 plus f prime of 0. I know I keep writing this. You're like, dude, I already know. Yeah, but if you do this, you're going to get the pattern down really well. Just following it. And then f triple prime of 0 over 3 factorial times x minus 0 cubed. And then we pop everything in as such. But we already know what this is. I already know P2. P2 is right here. So I'm not going to plug all that stuff in. I'm just going to say, hey, dude, it's x plus what's f triple prime of 0? f triple prime of 0 is -1. Over that 3 factorial. Does anybody know 1 times 2 times 3? That's 6. And then we have x minus 0 all cubed, so that's x cubed. So we can say our third term, we can maybe call this x minus 1/6 of x cubed. That's a cubic. That's a good cubic. So it looks like we don't end up with any quadratics. And then we can look over here and say, there's your cubic approximation. Where what's in black is sine, it looks like a better approximation. It looks like we can get closer and closer. We're almost getting out to -pi/2 now. Where our first linear, we kind of diverged from the line about here. Nowhere near pi/2. This one's getting freaking close to the pi's/2 with a really good approximation. Now, if we continue doing this, I'd rather look at the pattern. We're going to get a better and better and better. So if you look at what's in green, this will give almost a perfect approximation all the way from -pi to pi. It's a better approximation. If we continue doing this forever and ever and ever, it'll be damn near the same thing. So now I'm just going to run through and just do P7. And you're like, oh no, how are we going to do P7? Well, have we noticed that we lose our center terms? We've gotten, here's our P1, here's our P2, here's our P3. What's P7? Well, since I already know P3, it's x minus 1/6 x to the third, and now we're left with our fourth derivative of a over 4 factorial times x minus a to the fourth. But we already know what's happening on each one of these even terms. It's 0. It's just 0. So I'm going to skip all of the even terms and just write in the odd terms. Following our thing, which was going to tell us that this is going to be f to the 5th derivative at a, 0, over 5 factorial times x minus 0 to the 5th, plus our 7th derivative at 0 over 7 factorial times x minus 0 to the 7th. So I jumped over P5, and we're like, all right, so it's x minus 1/6 x cubed, and then we have, well, what's the 5th derivative? What's the 5th derivative? It's 1. So that is plus 1 over 5 factorial times x to the 5th. What's the 7th? Oh, it went back to -1. So let me just change that sign. Let's make that negative, and now we're going to have 1 over 7 factorial. Yeah, and that made it better. Just draw right on top of it. I'm sorry, I suck. And that's x to the 7th. Now, I don't really care what 5 factorial is and 7 factorial, but we can see that we're getting a better and better and better approximation. As we continue on, it will just be an amazing approximation. And if you really wanted to clean this up and look at that, there might be some sort of pattern for x. This is x over 1 factorial minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Dude, that seems like there might be a pattern emerging that we might just be able to say, oh, Sine, let's go, it's this. Can't you write that? Doesn't this look like a sum? From k equals, I mean, you can start at 0 if you want to. Let's start at 0, and let's go up to 7. It looks like it's just, wait a second, what could we do? Maybe we could do this. X to the, you know what? Let's just wait. You've got enough. We're already 15 minutes into the video. I'm looking back at my work going like, do they understand anything? But the game is, the more approximations you have, the more terms you go to, the better the approximation. You can look, we went from linear, pretty close, cubic, pretty gosh darn good. But then we start getting into 5ths, 3rds, 7ths, and they get really good approximations. There it is. We'll do a Taylor expansion for e to the x next. And then I think we'll start giving you all your different formulas. See ya.